oops, there we are. So let's say that we wanted to write a program that would be able to tell the difference between an apple and a banana. So let's just think about how would we approach that problem? And how would we start? I mean, I don't mean the logistics of working with an image, but just the logic of recognition. And the first thing obviously is how are they alike and how are they different? And I can look at it where, maybe their position on the image is slightly different, or the shapes is certainly different. But I think the what jumps out at me most obvious is color. So we can start with that, and we'll say that if it's predominantly red, it's an apple, and if it's predominantly yellow, it's a banana. And hey, it works. So we can now successfully tell the difference between an apple and a banana until we see something like this. But color is still a valid differentiator. We can handle this variation. So we'll just adjust our program to say that if it's predominantly red or this shade of green, it's an apple. And if it's predominantly yellow or this shade of green, it's a banana. And hey, everything's working great again, and we can tell the difference until we see this. Then maybe color's not the only metric. Maybe we have to look at something else. So maybe we can revisit shape. That was a good one. And if it's predominantly red, this shade of green, or round, then it's an apple, and so on and so forth with the banana. And that's great until maybe we see a partial image or a shape we can't categorize or something. You probably see where this is going. And the point is, you quickly get into this endless what about this game, where every rule you have has an exception, which spawns more rules, which all have exceptions, and so on. And I would suppose that it's possible to write a program where every conceivable variation is accounted for, but then let's say you add an orange, or you substitute for an avocado or something, and then you have to start all over. And that's where machine learning comes in, where the computer goes through the what about this and figures out the rules for itself. So today, we're going to talk about machine learning and a bit of how it works. We'll look at the importance of data, or the lifeblood of machine learning. We'll look at learning types and algorithms, and we'll go through a demo so you can see for yourself how to do it. And spoiler alert, it can be pretty easy. So if you know nothing about machine learning, you're in the right place. And what I hope you get out of this talk is an overview of machine learning principles, why it's used, and the basics of how to do it. And again, my name is Mark Kalal. I'm in software development. And there's my email. Feel free to reach out. And I can also be reached on Twitter as well. I don't post a whole lot, but I do tend to read. And if you want to follow me, I'll follow you as well. All right, so let's crack on. So what is machine learning? Machine learning, it's actually been around for a long time, decades in fact, and it was a term that was first coined by a computer scientist called Arthur Samuel way back in the 1950s. And he was working on computer programs that would learn how to play checkers. And he had the goal of a computer beating him in checkers. And it's sometimes called programming statistics, although it's not exactly statistics, although it does heavily rely on statistical methods. And it's sometimes called artificial intelligence, or AI, which technically it is, but machine learning is more of a subset, where AI is the entire field dedicated to making machines smarter. And machine learning is one way to get to AI, where the machine does the same thing over and over again, tweaking a bit each time until it gets the answer that you want, just like a person learns from experience. And what does that mean? Well, if anyone's tried to learn a sport or played a musical instrument, you probably weren't very good at it at first, but you practiced. People showed you things, you watched other people, you read about it, and all these different things kind of filtered in your brain, and we just call that experience. And by contrast, computers, of course, they require very specific instructions. And most of us are developers, so we understand this intuitively, that when you program a computer and write an application, you're implementing a problem that you yourself have already solved. So with machine learning, it kind of sits in the middle, where it's the idea of a computer using this data as experience for determining actions. Or more to the point, computers using experience and algorithmic processes to progressively improve their performance. And there's a name for this learning from data. It's called training. It's a very central idea. We'll go into that in a bit. But the definition, I can't remember who wrote this. I think it was Andrew Ng. I love the definition. An application of artificial intelligence that provides systems the ability to learn and improve from experience without being explicitly programmed. And from a business application standpoint, machine learning and AI contribute to a broader field called data science. And we could think of data science as using data in ways that generate business value, where many data-related topics all work together. And the ultimate goal is this notion of insight. And if we think about that, like imagine that we work for Target and we have the buying habits of everybody in Minnesota, for example, and we have that at our disposal. And we can all agree that that's probably worth a lot. But then as we start segmenting that out, and let's say that as well as a year, we have the buying habits of every month and maybe every week or every day, every time of day. You start looking at those different dimensions and different pictures emerge. And so all this data provides those different insights, which of course suggests things like what merchandise you stock or your sales promotions, and which ultimately drives goals like increased sales and customer loyalty. There's a number of reasons why we care about this. So to begin with, this information insight is available very quickly, near real time in most cases. And this benefits the industry as a whole and not just sales and marketing. In fact, I was recently reading that machine learning systems were being applied to stock market data, as the systems could outpace human analysts. I'm pretty interested to see where that leads. And I mentioned that machine learning has been around for decades, and the recent adoption is believed to have been due to the rapid increase of computing power. And the same, I'm sure you've heard the terms deep learning, neural networks, and those terms have been around forever as well, just that machines really weren't powerful enough to do anything with it until now. And there's some concerns, just as well as we talk about what machine learning is, we talk about what machine learning is not. And machine learning systems, they tend to be designed for a specific design and purpose, but even that's getting broader. And there's a lot of concerns around, like what more machines do for us, if there's any equal or opposite reactions, or maybe better said, sort of unintended consequences. And I know a popular thought is, our jobs will all be done by robots soon. But there's items where things don't turn out as planned. And there's some really funny examples. There's one I had a video, I wish I still had it, but there's a robot hand that was learning to pick up a cup from one side of a table and carry it over and drop it on the other side of a table. And the computer learned that rather than work through the mechanics of grasping a cup and lifting it, it could use the arm to just shove the table to put the cup in the same geolocation that it would have been had it moved it. I thought that was pretty clever and funny. And there's some more iffy examples, like the man who went to the zoo and took pictures of all the animals, and then he uploaded them to his favorite social networking site, and the site was tagging the photos as his friends. So this big gorilla showed up as his friend Greg. It was, a pretty interesting scenario. And then some are simply scary, like the story of the young girl who was going to have a baby, and she was using the family computer to research, whatever she was looking up. And shortly after, the family noticed they were seeing all these pediatric banner ads or baby coupons and things, and they were wondering what was going on because she hadn't told her parents yet. So it was like a huge invasion of privacy. And a lot of these things, it's not necessarily a black eye on the technology because, bugs got to be worked out, but it certainly was a PR disaster for those companies. But the point is that estimating these sorts of consequences and figuring out what to do about it is a question that we need to think about. And then data transparency is another good one, because with very few exceptions, really nothing about AI or machine learning is simple. In fact, quite the opposite. It tends to be very complicated, black box, and it can be difficult to understand the inner workings. Even tech pros like us don't always get it. And this isn't a unique criticism. You could say the same for cars. How many people really know how their car works? But the big difference is that machine learning is starting to contribute more and more to decisions that affect your life. And there's one, I'm sure you've all heard by now, the GDPR, General Data Protection Regulation, that's going on in England now. And there's language there that addresses some of this transparency, where algorithms have to be backed up by a person. So if you get denied for a loan, for example, you get to have a person sit down with you and explain why. It can't be just the computer told me. And with that, let's move on to data. I cannot hear thunderous laughter, so I'm assuming that this is weird. It's like my leg falls asleep and trying to scratch it. I got no feedback. All right, where's the button? All right, let's move on.
I can unmute everyone.
Oh, no, it's fine. I'm just trying to be funny.
Okay.
Thank you, William. Well done, sir. Okay, all about data. So data is a fuel for machine learning. Say it's the purpose in the vehicle, the paint and the canvas. And as a general rule, machine learning thrives on a large and accurate pool of data. So having data, getting data, and knowing about data is a very important prerequisite. And I think data is really the hard part of the entire machine learning exercise. In some cases, this is easy because data is everywhere. And more data is always better. And collection efforts are nonstop. The storage is getting cheaper. There's really no reason to delete anything, is there? And there's an interesting statistic I remember that if you consider all the data that we've had since the beginning of time, 90% has been collected over the last 2 years alone. That's an insane number, 90%. And that's expected to increase, and it's a phenomenon consistent with what futurists call accelerating returns, where all this data leads to capabilities to capture and record even more data, which leads to capabilities to capture and record more data, and so on and so forth. And we have data, what can we do with it? Well, we can do something useful with it and use to make new services or improve existing services. And a lot of companies are doing that, especially internet companies. And we can look at a couple examples. So to begin with, this email spam filter is a classic example, and we all use email. And I'm sure our email clients all have spam filters. But how does it know what emails should be delivered and which one are spam? The only answer is it has reams of emails to look through, and it can tell the difference over time of what are the characteristics of spam and what are not. And let's say you take a picture and you upload it to Facebook, and Facebook's able to tell you not only if there's someone in the picture, but it can tell you who it is. And furthermore, how is Facebook able to suggest friends based on the profiles you've seen, or any mutual friends, or even the places you visited? Now, Facebook's been in the news over the last couple of years, so we know they have lots of data that they use at their disposal. And then you buy something online and you go to pay through it through PayPal, and how does PayPal know that this transaction's legitimate, or how would it recognize it as fraudulent? And of course, they have a whole history of transactions and can instantly tell if something looks a little different. And there's a lot now, I think the medical industry, there's a lot of imaging with machine learning being used to diagnose diseases. So it's getting very, very popular and more common. And this is a famous chart where different machine learning algorithms were used to solve the same problem. And the lines in the graph, these are the different algorithms that were applied. And the x-axis here is the amount of data that was being used. And the y-axis is just how successful they were at predicting whatever it is they wanted to predict. And initially, starting to run their tests, you could see a pretty wide spread. But interesting enough, as more and more data was applied, the accuracy increased, which you would expect. But what's interesting about this is the accuracy all kind of grew in concert. So the accuracy, there was more consistent as well as being more accurate. Except for this, I can't remember what this one was, but I don't know what was going on there. Control case maybe. But the point is that this graph suggests that the higher volume of data you have, the less important the specific algorithm you use. So another thing that, when it comes to data, more is more. And we can't talk about data without discussing the popular word of big data. And big data generally means one or two things, or maybe both. It's a giant mound of nebulous, shapeless data, maybe from different sources, but just a huge blob of data. And it also means that data that, for whatever reason, cannot or can't be processed through traditional tools and methods like relational database, for example. And how this relates is important, and whether or not data is considered big data is subjective, but it's usually characterized by what's called the 3 V's. And the first V is volume, and this is just the sheer mountain of data that's consistently available. And next is velocity, and this is the speed at which this data is coming at you. And these two alone paint a pretty scary picture, I think. I can imagine myself being at work and loading up data, and the boss says, we need to start on the data from today. Say, but boss, I'm still working on the data from yesterday, and now the data from today is here. It's even larger than it was yesterday, and it's coming earlier in the day. Well, that's a problem that you're never going to get in front of. And then last view is variety. And this is an interesting one, if you think about it, because just in my world, the information that I work with, it's not just numbers and letters. XML files, JSON files, CSV, not to mention like documents and Excel files, but there's also images, video files, sound files. And matter of fact, very recently I was reading about where someone figured out a way to process odors. So someone found a way to serialize an odor. I can't wait to learn more about that. Far out. And we have this data, and where does it come from? So if you don't have it all, there's lots of places that you can get it. So most of us work where we have databases available, or maybe we manage applications that have logs, and there's information there. And a lot of this information that might not be directly used, and there's some creative use cases have spawned from it. And might be data that's the result of a calculation, for example, or leftover data from a particular process, or remnants from user actions, for example. And this ancillary data, or data exhaust as it's sometimes called, a lot of people have wondered it can provide value, and yes, of course it can. And as a classic example is when you hit a web page these days, the web server that you're landing on, it can track and it knows what device you came in on, the OS that you're using, probably even the version, I can't remember, and a bunch of different things that has nothing to do with the page itself. So yeah, there's a lot of value that can be grabbed from that. And then there's some data you can get. So there's a lot of information available on public sources. Then the government sources, there's financial data, a lot of climate-related data that you can use for projects. Kaggle has a lot of data sets for a variety of different things, and that's all for free. And then Internet of Things sensors. This is huge. A lot of things that are fueling automation, factories and robotics. And we mentioned self-driving cars. That's a great example, because that produces and absorbs data at just an absolute alarming rate. And then, of course, there's things you can ask for, and your Twitter followers or Facebook friends, and then there's anything you can convince a user to tell you. And there seems to be a playbook that's forming around this sort of thing, where the sensitivity of what you're asking for is commensurate with what you're offering to give in return. So fill out this form for this white paper, for example. And I kind of live in a compliance area, so there's a couple notes on that about privacy concerns and the data that you use for that. So one of the practices there is anonymizing data. So, do you need to know that it was Mark Kalal that read this white paper, or can it just be some dude from Minneapolis? So it's just assuming that at some point you're going to be asked to hand it over and only store what you need to store. So with that, let's move on to learning types. Oop, and I see a QA. Oh, no, I don't.
I wanted to say one thing.
Oh, yeah, carry on.
Just to add to your presentation, big data almost always represents people.
That's a good point. That's a great point.
That's all. Thanks.
No, fine. Big data. Oh, there. Okay, cool. I will leave this window up. I'm running out of space to put things. All right, carry on then. Oh, go. There we are. Okay. Excuse me. My wife said, boy, that cough sounds bad. I said, I'm hoping you'd say it sounds good, because I was up all night practicing it. Okay. All right, learning types. So we talked a bit about what machine learning is, and now we'll talk about how things are done a bit. So a few different learning types, and we mentioned training, and the key tenet is this concept of training. And the general goal of any machine learning system is for the computer to perform well with data that it's never seen before. But in order to do that, it needs to be trained. So what and how this training is done is a key factor that separates the different learning types. So we'll just walk through supervised learning in a couple flavors, unsupervised learning in a couple flavors, then reinforcement learning. So supervised learning, and all the learning types involve training in one way or another. And with supervised learning, the data and conclusions are known. So the computer is asking questions of the data that it can see the answer to. And this is called labeled data. So it's looking at the different fruits, for example, and it's examining an apple and learning what makes an apple an apple. It knows it's an apple, so that when it looks at a fruit, it can categorize it effectively. Excuse me. There's a couple flavors of supervised learning. First is classification. And this is where you're looking for an answer that's categorical, like yes or no, or apple, banana, orange. And then regression is where you want an answer that's a real value, like a number or a trend or whatever. So will I get a raise this year? That's a classification problem. And how much will my raise be? That's a regression problem. So let's look at an example. Classification, of course, the textbook example is an email spam filter, where emails have certain characteristics. And it might be something that there's something in the subject that looks off, or the header might be something, and all spam emails have this in common. And so the computer learns over time that if these characteristics are present, it's probably spam. And I use my Microsoft Outlook. Some of you may as well. And there's a feature like a feedback loop there where I can flag something as spam that might have slipped through that initial filter, which circles around and makes it smarter overall. But anyways, it's got this data to compare to, and it looks at these characteristics to figure out if it's spam or not spam. In regression, in this example, we want to calculate the amount of rain that we're going to get. So we've got historical data of the temperature, wind, overcast, and from that we can tell how much rain has historically fallen. So when we're encountering new data, we have a basis for its predictions. In unsupervised learning, this time we use what's called unlabeled data. We don't tell the computer that the data is apples or anything. Matter of fact, it's not important to have any information about the data at all. And the strength in this one is not in predicting values, but in discovering patterns. And very recently, I was having a discussion with one of my colleagues, Michael, and he's just an absolute football nerd. And we were talking about that. I said, Michael, if you had a list of all the players and you showed me who has thrown the ball the most or thrown it the farthest, who's kicked the ball the farthest or kicked it the most, and who's ran it the most, I could tell you who the quarterback is, who the kicker is, who the running back is. I don't even need to know that it's football. It doesn't even matter because it's just categorizing based on those differences between each other. And a couple flavors there, or clustering. And this is where there's groups of things that are based on similarities or differences between other things. And then association, and this is occurrences or the probability of occurrences in data. So when the list of people in Edina who saw the rise of Skywalker is clustering. The people who saw Rise of Skywalker and Terminator Dark Fate is association. So we'll have a look at an example of those. So let's say that we're working at a communications company and we're trying to segment our users to figure out what offers we can give to the people that are most likely to value them. So we can get a list of all the people that have used their phones a lot, but maybe not much internet, people that use the internet a lot, but not so much their phones, and people that use both. And this is an easy way to say, okay, we're going to give these people a deal on phones for a month, and we'll give these people a deal on internet for a month to try to bolster usage or target them in any other fashion. And then association, we've got customers where, this person bought bread, eggs, and milk. This person bought bread, fruit, and milk. This person bought bread and butter. Well, the pattern, maybe they forgot their milk, or maybe we can suggest that to them. And association is one of the keys that Netflix uses for their movie recommendations. Only it's not bread. It's the type of movie, the genre, your profile, watch history, things of that nature. All right. And lastly, reinforcement learning. This works a little bit different, where there may or may not be an initial training step, and it requires a constant flow of data. And so this is where each action is performed. Then you get feedback on actions, which helps make the decision on what the next action should be. I mentioned that Arthur Samuel, the father of AI, he was trying to teach a computer how to play checkers, and this is the method that he used to teach the computer. And his ultimate data set was a book that he had, and it was a book of known good checkers moves. Like to be a great checkers player, you'd use these moves. So when the computer made one of those moves, he would mark it as a good move. When the computer did not make one of those moves, he'd mark it as a bad move. So over time, the computer learned to emulate the moves that were in the book. And yes, the computer was able to beat him playing checkers, quite regularly, in fact. So with that, let's move on to algorithms. And as there's, in terms of machine learning algorithms and ways, there's a list as long as your arm. But for now, for the rest of this talk, we're just going to look at some of the ones in supervised learning since they're the ones that are the most straightforward. So we'll start with a couple. Decision tree, and this is an interesting algorithm. And this is one that's good for classification problems, and it divides its segments data by conditions. And then linear regression is one where it expresses information in a linear format. So if we start with a decision tree, we'll use an example of we want to tell these fruits apart, the apple, the banana, and the grape. And the basic premise is to get down to an accurate classification. We want the highest accuracy or the highest probability of being right. And there's a whole family of these types of algorithms, and they've all got their own way of doing things. But the general pattern is to iterate through all the features and all the attributes and figure out what questions to ask in order to break it down. So let's see an example of how that works. So we've got a very simple data set here, and we've got two attributes, color and size, and then we have what the class is, an apple, a grape, or a banana. So we can look at that and figure out what question we want to ask. So we'll start with size. And we'll say, is size greater than or equal to 3? And if it isn't, just from our data, we know with 100% probability that we've got a grape. If it is, well, we don't know, so we have to dig a little bit further. So we can ask another question, and that is, how about color? Is color yellow? And if it's not, then we know with 100% probability that we've got an apple. And if it is, well, then we don't. There's really no other questions we can ask, and there's no other data we can compare to in this particular data set. So the computer essentially just flips a coin since it really doesn't know. Now, the data can be expressed in many different ways, and like, for example, when weights come into it, where yellow apples aren't nearly as common as bananas. So you could say that if you have a fruit that's yellow, it's more likely to be a banana. So when those type of weights come in, then you have a lot more things to play with. And not to mention that this is just a small data set, and I did this on purpose just to illustrate it. Now, linear regression, the classic example is with house prices and how those are factored in. So we've got a house here, looks like nice suburban house, looks like 2 fireplaces, nice big trees. So we want to see how much does this house cost. So what we can do is do the comparison. And we'll draw a reference between what other houses are in their prices, and we'll organize those in a linear fashion. So on one end, we've got a very small house out in the country, which we know is going to be cheaper. On the other one, we've got a huge house in the city, which we know is going to be a lot more expensive. And since our house fits in the middle, we can kind of see a relationship forming. So if we look at that, how many of you would have guessed it'd be about 350? That was my guess. And with that, we will move on to how we can use machine learning. Cool. All right, so, whoops. Thanks, Will. This is my favorite.
I like that. I like this as well.
Yeah, this is my favorite one, by the way. Excuse me. Good. Okay, machine learning pipeline. How do all these things tie together? All right, well, the first step in doing an application like this is start with a question or problem, or look at data you have and see if it tells you anything interesting. And then collect data. Now, again, I mentioned that data is a hard part of machine learning, and I, for this example, am greatly oversimplifying this particular step. There's a number of things that go into quality data that you're probably aware of. If there's any missing values or something that's obviously wrong, scale is an important consideration. Like we mentioned, the house sizes. A house in Minnesota, for example, would be based on square feet. And a house in England, for example, might be based on square meters. And you have to find a way to put those two where they're on equal footing, or else nothing's going to come out right. So knowing your data, collecting your data, that's an important step. There's lots of tools available to do this. Then second step is modeling, more the statistical model, I guess. And the modeling, there's a couple steps with that, where querying the data and getting to know it, and a feature extraction, what sort of attributes are important to focus on. One step here that like if you've got alpha data, converting it to a number. I'll show you an example of that because some engines don't work well with that. And then the first time you interact with your machine learning model and data is the training step. And this is where the computer chews through it all and fits it a certain way. And I stepped back. There's a testing step that I don't really talk about too much. And an important step of training is testing to see the accuracy of the training that you're doing so far. And there's a lot of ways to do this. Some common ways are to have like 2 data sets. One is for training, and then one is to do a quick test and see how it fares. Another common way is to split your data set into a certain percentage. Say 90% will be training, and I'll withhold 10% to be testing. Cross-validation is another common way where you might do several passes through, but then segment off a certain percentage each pass through of different data, and then just take an average at the end. Lots of ways to judge the accuracy of your training. And then lastly, of course, use the model, do what you want to do, which is classify or recommend or predict or do whatever. And then of course there's a loop, if you encounter more data, or retrain to try again. So that's the basic steps now. It's just a real high level view. And there's a lot of tools that we use for this nowadays. We're going to look at a demo. We'll look at ML.NET, but there are lots available. Microsoft Cognitive Services, Azure as machine learning. There's a lot of services available. TensorFlow from Google's another popular one. Again, there's lots, and there's even more coming out. It's like every software vendor is either adding machine learning capabilities to their platform or coming out with something similar. So let's have a look then, and we'll go into ML.NET. So we'll look at a demo. I'll try to keep this up. So look at GrabMinute, data files and formats, look at some APIs, the model builder, and some sample apps. So let me tab over, I think, oops. I'll just drag this. I've got a multi-monitor setup, so I'll drag this over. Cool.
Quick question for you, Mark.
Yes, sir.
Is ML.NET compatible with Xamarin? Do you know?
Probably.
I feel like. Oh, go ahead.
No, carry on.
I was going to say, I feel like at the Dev Summit that we were at last summer, there was a presenter who did something or did a talk on something similar, and he was saying at the time, at least, that it wasn't, unless I misunderstood.
That's interesting. Well, here I'll tell you what I know about it. And what I love about this particular tool set is the overall implementation can be componentized, or libraries. So you deploy it as an application along with something. You can deploy it as a cloud service, with an external API. So being unfamiliar with Xamarin, I'm not sure if there's any restrictions to that, but if there's a server component, I'd be surprised if it didn't work. But again, I guess I don't know for sure, but that's just my take on it.
Okay, cool, thanks.
Sense? Cool, yes.
So is it .NET Standard 2.0 or what?
.NET, what do you mean? ML.NET, you mean?
Yeah, does it come in as a .NET Standard 2.0 NuGet package?
Oh, thank you. Yeah, the installation. Yeah, let me show you. If I hang on, my banner just blocked it out.
Okay, if it does, it'll probably run in Xamarin.
Yeah, I'm going to look. We'll go to NuGet and we'll see. Because that's how you install it. Just there it is, ML. Mm-hmm. So yeah, just I forgot the command, but you can search it and install it. It's very, very easy, and it runs.
Cool.
Dig it.
Thank you.
I'm going to maximize this. Okay, so you know what? Let me jump ahead. Well, we'll go through the program code line by line, and I'll show you how I did this. So I did 2 examples. I did the classification, trying to use a decision tree to show an implementation of the example we just walked through, and the same with the linear regression. So to begin with, where's my data? Let me show you the data that I had.
Mark, will you zoom up a little bit when you go to the code window?
Yes, sir, I can. So can you see this data window all right? The notepad I've got up, can you see that okay? Yep,
yeah,
cool.
A little small.
Okay. All right. So this was an example I was mentioning earlier, and this data set was just something that I was using. So this is meant to carry on from the example we saw earlier. We just have very, very few attributes trying to identify a fruit. And in here, the color is represented as a number. And I don't remember exactly what I did. I think red 1 was probably red 2, I think was green, and so on and so forth. I mean, you don't need to, the colors itself are not important. The fact that they're different is. So the numbers work just as well. But I hope you can kind of catch what that is, but that's how this data set works, and that's all it is. So if I look back here, now in the program code, there's the base root object of it all is this thing called a context. And that's like an umbrella object, a container object that every operation goes within. So everything tends to stem from this context. So in this implementation, I'm just doing it from that flat file data. So I'm just locating where the data is. And then a lot of this program code, I just cookbook together from samples that I found in the documentation. So going through it, creating our context, which is our umbrella object. Then we loaded data from file, which is just a plain old comma separated file, nothing fancy.
Mark,
Yes, sir.
sorry, zoom that up.
Oh, of course. Oh, sorry, man.
That's pretty small
Got it.
for the older people in the crowd.
No problem. Apologies. Is that okay?
Yeah, that's
Yep.
better.
Right on. Okay, where was we? Oh yeah, configuration. Now this part here, how do I explain it? So in order to, you need to pair your data with what the algorithms are expecting. And I mentioned about conditioning data, and ML.NET contains a huge variety of ways to do this. I find that a lot of text processing works fine. Good old awk and sed can be used for a number of things, so you don't have to rely on the tools here, but you can if you like. But this step here is I'm basically mapping the data in that file to what the algorithm is expecting to see. And it's looking for a concatenation of the features and the overall class that it applies to. And that's what this set's doing. And then here we have this thing called a pipeline. And that's basically saying that this algorithm and set is going to be tied. And then our next step is we do the actual training and this fit method. And this is the first time that is interacting with the model. And when we run through, you'll see it run. And then once we've got the training done, we're using the same train model to do a sample prediction. And so to do this, I've just created a different fruit object with just some random attributes just to see how it fares. So let me jump down and I'll show you what those classes look like right here. So fruit, again, just like we saw in the data, they're just the color, size, and then the label, the class of what it is, that's all. And then I made a prediction class that we're using to feed into that prediction engine to spit back what label or what class that we think we've just predicted. All right, so let's give this a run. Let's see how it fares. I've set a breakpoint here, so we should be able to step into it easily. All right, so let's go through. We're going to load up our data, create our context, and then map everything. Assign the algorithm. Now here's where we train. I'm going to hit go, and it's running. It's giving her hell. We kind of push this way so we can see when it finishes. Yeah, training can take a while. And this is I don't remember how many. I think there's like 60 data elements out. All of this is pretty small. But of course, my computer's not really set for this sort of thing either. All right, so there we are. So now we can do our prediction test. So we've got a trained model. So we're going to create a piece of fruit that has a color of 2, which I forgot what that was, and a size of 3. So we're going to spin this out and spit out our prediction. Yay, that was fast. So let's have a look, and I'll just write out to what we think it is. And where's our window? Here it is, right here. Orange. So we entered it, or at least it thinks that it's an orange. Cool. All right, so let's carry on to regression then. I'll just step through this as we go. And you will notice that the format and the form is shockingly similar because it is identical. Again, the pipelines and the way you work is identical. So in this case, I'm going to show you the data first. Well, if I can find it, there it is. So the house data, we're looking at it a bit differently. This is a little bit broader. There's still what, 60 records. There's still not much of it. But we're looking at the size of the house, the size of the yard or the land, how many bedrooms, if there's granite in the kitchen, if there's an extra bathroom, and then the price. So just a handful of attributes that would normally be used to differentiate houses with. And then I'll jump down and just show you what the class looks like. Shockingly, it's identical to that. where we just have the different attributes that are mapped out. And then again, a prediction that we're using for the price. So as I step through this one, regression, there we are. Okay, so we're going to load the data from a file, create a new context, load the data file. Now this one, our transform is a little bit different. So we're mapping everything and loading up. And then we set the algorithm to a regression. Now I want to say a point here because the stochastic dual coordinate ascent and then the classification one was dual coordinate ascent. That obviously isn't a plain old decision tree or linear regression. And I tried to find examples of that inside, and I couldn't find it. And that kind of begs the question about what's the best way to map a particular algorithm to the task that you're doing. And I know what I do. I mean, you'd like to think that there's a scientific way that you can arrive at that'll tell you absolutely. And there probably is, but myself and everyone I talk to, you do it by trial and error. You just run through it and see which one performs the best, go with it, fine tune it, try again with something else. That just tends to be the way that it's done, or at least the way that I've done it. So anyways, so we've got our information loaded up. Now we're going to do the training. Oh, that was fast. That was really fast.
Mark,
I think. Oh yeah.
would you say that ML is is there a lot of art form to it, or is it a hard science?
Oh, that's a good. Well, there certainly is for me. You know, well, we're going to look at a couple different things because we're just looking at building a model, and there's a bit of art involved in there, at least in terms of what results you're getting from what you're putting in, and it's the variables, man. So the data set I showed, was just in no particular order. It was, I think I may have organized it just so it looks pleasing when we see it, but it certainly doesn't have to be, or it might not have to be. But that might be something to test. If I do this in a different order, is that going to affect the results? That might be something too. If I pass it through a different algorithm or tweak things a certain way, that may have a different answer. I mean, there's certain, and this tool is capable of more than I'm showing. Like when we go through our training, there's metrics that can be spit out to show the accuracy, and there's things you can do to tweak it and rerun it to see if you can improve the accuracy. So there's a bit of science involved, but I think a lot of art. It's just trial and error to see what works the best. Yeah, does that make sense? All right, cool. All right, carry on then. All right, so let's see. Okay, so we're going to create a new house with just random information of the size of the yard, and so on and so forth. And create our engine, run our prediction, and now let's see what it is we've done. Where's our window again? And hey, so the price of this house weighed in at 142,000. Neat, cool. Okay, and then I'm seeing a note from author. Yep, I have heard that data prep cleansing most. Yeah, I think so. I agree with that 100%. Everything with data, that's the hard part. And it's the same garbage in, garbage out. And even I've got another example that I'm going to show that may illustrate that even closer. But just the scale problem I mentioned earlier, where if we starting putting houses in that are measured in meters instead of feet, and we treated them as the same, you've greatly skewed the answers that you're going to have and the reliability as such. So again, knowing the data and catching those things is extremely important. So yep, Arthur, completely agree. Okay, so I think that's it with this. All right, so any questions or anything on this particular demo before I jump to the next one?
Yeah, a quick one about just the difference between classification and regression. Are these two different training styles, or what's the difference between what you're doing there? I realize that data sets are different too, but here's about the names.
Yeah, good question. I guess, yes, different styles. The one that this classification is considered multi-class because there's more than one particular answer, but it's categorical, meaning it's going to be an apple, or it's going to be a grape, or it's going to be a banana. Okay. And in a regression standpoint, there's a range that it can land on. So
I see.
Yeah. Now the training, how the training happens, I mean, that's kind of black box as far as I know. I mean, there is an answer, and I'm sure we could dig up exactly how this training works and the idiosyncrasies of these algorithms. And again, there's a lot of attributes and settings that are associated with these, and a mind-boggling amount really that you could fine-tune to try things. But yeah, they're fundamentally different in terms of the answer that you're going to get out of it.
Okay, cool.
Yeah.
Thanks.
My pleasure. All right, so I'm going to put this one aside momentarily, and let's have a look.
One question.
Yeah,
Sorry,
yeah.
Mark.
No,
One more question.
by all
Could you
means.
show me what version of the NuGet are you using? Because I just noticed that the I think it's 1.5 something was in preview. Are you using a preview package or using like the 1.4 stable?
Oh, for ML.NET?
Yeah.
Gosh, that's a good question. That I don't know. Yeah, 1.4 is
Okay.
what I should be using. Oh, that's it. Oh yeah, now I see it. I wonder why. Or 1.11?
Are you using 0.11? Is that right?
I'll be darned. You know, this is funny because earlier today, I did an update because I'm using Visual Studio 2019 Community Edition. And I did an update and I'm thinking, hey, I'll just update it. What could go wrong? You know, but now I'm noticing, I never noticed that before. I thought I was using the latest version, which is 1.4. So now I'm puzzled where that's, yeah, gosh, that's interesting. I don't know why.
Yeah, and on NuGet, they've got 1.5 preview 2 out, but that was only 8 days ago.
Yeah, I don't
so I
think
was just curious.
That's interesting. Oh, goodness. Gosh, I guess I don't know. No, good observation. I don't have an answer for that question.
Thanks.
Yeah, sorry, man.
Nope, that's good.
Cool. All right, well, let's jump. So I've got a demo here that we're going to use, and we'll say that this is just going to be running of what people thought of this talk. And I appreciate any and all feedback, so I shall do it on your behalf. So let's say Alan. Alan said, I like the demo. Oops, demo. And we'll add this, and we're just going to echo the comments back. And thank you, Alan. That's such a nice thing to say. And we'll say Tom. Whoops. Tom.
Intriguing.
Yeah, great job. Great job.
That's hard to spell.
Yeah. Smart Alec. Yeah, great job. Thank you, Tom. Oh, thank you, Tom. Great. And let's see. Adam.
Loved it.
Yeah, Adam loved it.
Aw.
No. Why, Adam? Oh, what kind words you had. That's just great. Let's see. What does Steve say?
I would never say that.
All right. I'm paint dry. Yeah, I'm trying to have fun with you. This is a kind of a silly demo. Yeah, okay. Well, you probably figured out what that's doing already. So what I want to show you next is, this is a cool model builder. So the example we just saw was a way that you can use program code to build your own models. But there's also one, and this one I think still is in trial, and it's a model builder. And I think this one's extremely cool. So I'm going to put this aside and we'll walk through this one. I've got a different project here. If I can find it. That's the one right there. Okay. And very imaginatively titled Core Web Application 1. Okay, and this is an example of a method called sentiment analysis. And what this is this is looking at a text string and it's trying to determine, is this positive or is it negative? And that's essentially what sentiment analysis is what's the general feel of what it's looking at. And I built this one with the model builder. I'm going to show you that now. I'm going to stop this so I can have a look. And the model builder, there's a lot of, I think you can install that. It's just a plain old Visual Studio extension. You can install it from here, excuse me, or you can install it. A couple ways you can do it. Let's see. Where is it? It's here. I know it's here. There it is. Okay, model builder preview. And once that's installed, you can add that to any project simply by clicking on it and saying add, and you can add machine learning. Now I'll just show, I'm not going to do it because it takes quite a long time, so I won't do it, but sentiment analysis is the one I chose. But you can do classification, recommendation, image. Well, image is a little bit different, but there's a lot of things that are available just at the ready, or you can choose to do something, whatever you want. But this is like a point and click sort of way to build a model in the same way that we would have done it with program code. Let me bring this up. So if you need, oh, that one can't. Sorry, man, I can't change the size of this one. All right, I hope you can see that okay. All right, I'm not going to do this because it takes quite a long time, but it walks you through in a wizard style to choose a data set, you train it, and then you can use it. So, but what I will show you
We can't
is,
see your dialog window.
oh, for the add data, what I'm looking at with the
Yeah.
wizard? Oh, what a shame.
No, I can see it.
You
It
can?
says add data and you can choose your input, right?
Oh, yeah, that's it. So file or SQL Server. Can you
Wait.
see that?
Is there a pop-up window that just came up?
No.
Okay.
No.
All right, then forget it. I thought you
Yeah.
were interacting with a modal type window that we couldn't see based on your mouse movement. Sorry.
Oh, yeah, no, it's all right. That's okay. Hey, first time doing it, those things happen.
Carry
Okay,
on.
yeah, so I guess, I mean, that's what I did. I followed the steps in this little wizard style builder, and it worked really slick. It took a long time, but it was like, what I will show you is, like we looked at using the model. So there's building the model is one set of topics, and using the model is yet another. And the two aren't really related. So in this case, the model code, it's just in a regular controller, because I just did a sample wizard project, nothing really. And then I added a method in the controller just called check sentiment, and then you pass in the value that the user entered. And in here, in contrast to the example we saw where we built the model and kept it in memory, there's a way to save it to the hard drive and then recover it, and that's what this thing does. So I pull the model that I've already saved and then use that to run the data on using this predict method. Excuse me. So that's basically it. And the answer, how it comes back, if it's true, meaning if the value is negative, then I just change it to a hard-coded positive one. So in theory, you could never enter a negative comment. And then if it's not, just echo it back the way that it was entered. And that's really it. I mean, the front end code is, well, there's really nothing to it. There's just an empty div and then just a plain old post that calls the method and spits back the return value. So nothing really fancy there. But this here, now this is an interesting one, and I'll show you the data because if I can find it. Bear with me. There it is. I have to drag. Okay, so the data that I used, this was from a set. Now there was one that Microsoft provided for their wizard, but there's like 10 records, and it was essentially useless. But this one here was from IMDb, and this was an interesting one because, how do I explain it? It's reasonable to assume that the comments that people make are a justification of the ratings that they did. So I can't remember who, I'd like to give credit to this data set. I can't remember where I found it. But I think what they did was they took, if it was a 1, 2, or 3, then those are negative comments. And then those were labeled as negative, which I think is a 1. Negatives are 1 here. And if it was like 8, 9, or 10, those were positive comments, and those were labeled with, was it a 0, I think? Yeah, 0, when it was 0. Now, there's some obvious flaws in that logic we can entertain, like Arthur, your comment earlier, because if someone, let's say, made a mistake and thought that number 1 was the highest instead of 10, then their comments would obviously skew your results. And then depending how often they did that in your data set would determine how skewed the results would be. So again, I don't know how to get around that other than kind of going through it and figuring those sort of things out. But anyway, that's the data, and that's the data I used to use this model with. So when you typed in, or when I typed in something, it would compare it to the sentiment that was arrived at from these comments and nothing more. Now we'll go a bit further. Let me change this around. Whoops, I don't want that back again. I'll just copy this so we can, and I will say that the return value is going to be, what do we call it? P-value. And then We'll just say negative comment. So then we can see it. And we'll do the same here. Just so it's very obvious to us what it's doing, we'll say positive comment. So we'll see the comment and we'll see how the computer reacted to it. And then we can do a couple experiments and see what happens. All right. Come on. There we are. Okay, so it doesn't matter. We can enter in like great job. Doesn't matter. That's something that we know is known good. Come on, good positive comment. Now one where you can do an experiment like I did with, and we'll say that was awfully terrific. Now if I see that, that to me, okay, awfully terrific, that, okay, that's showing as a negative comment. But when I see that awfully terrific, that's a positive comment to me. Or I can say that was terrifically awful. So all I've done is, whoop, maybe I spelled it wrong. That might be something. Well, anyways, so all I've done was swapped out the two words, and that completely changed the meaning of the sentence. But this model, cannot pick up on that. So you solve that by more training and additional scenarios to do that. And there's a few bits there. I mean, like I said, the ML.NET gives you some feedback on that, and there's some conditions around. Let's say if you've not done enough data, like we did with our fruit example, where you're forcing the computer to jump to conclusions. You know, there's a over or under training or underfitting, a couple ways that's described. Or you've done a plethora of data where there's no possible way the computer can come to the conclusion that it has, and that's considered overtraining. So there's a number of fallacies and things to watch out for that whole training step. And this was just what, like 25,000 records, I think. And the most accurate models are done with millions. And another point too, that what I love about ML.NET is you've built this model, and okay, I've did one. I did have this as a separate I'm going to stop this. I did this as a separate library so that we could see what the classes looked like if you wanted to see them. And this is all on GitHub too, by the way. But these are just done as zip files. I wanted to just hand rolling it into a particular location because I was doing so much back and forth, I got myself confused. So this is not a good practice. Forget you saw that. But anyway.
Hey, Mark.
Oh yeah.
We've got a question.
Oh yeah.
Are there preloaded models for common tasks like profanity filtering?
Oh, probably. Actually, that's a good point. With ML.NET, there might be. I know that there are with some of the cloud services like Azure Machine Learning and Cognitive Services. There's a couple flavors there. There might be an engine that you can use to train yourself, but more commonly in those deployments are pre-trained models that you can just pick up and use. You know, so you're using this second half where you're using the model that's been built and you don't have to worry about training the model. Now there's some obvious things to discuss there, because if you don't know what data was trained and where it came from, then the accuracy of the data that you're using might be in question. But the short answer to your question is yes, there are pre-built models available. I'm not sure what the collection is for ML.NET, but there are services like that easily available. Yeah.
Great, thank you.
Cool. Yep, that's interesting. I didn't see the question pop up. Oh well. Okay, where was we? Yeah, I think that's it. That's it for this demo. I mean, just having a model and dropping it in and using that model. And if I wanted to run this application with a different model, I would just have it point to a different one. And that's I think that gets to the first point you made about having this be available for other implementations, where if I'm just using this set of libraries to read and interpret a model, then the model could be theoretically located anywhere. And I could drop it in to change the behavior of my application anytime I wanted, just like any other configurable spot. Okay, so then I guess okay, then see, so we've looked at that. So, all right, anyways, then to just wrap it up, we talked about machine learning, the importance of data, and went through some learning types and algorithms and looked at examples and demos. So I've got, there's a URL list that you can click that'll give you all the resources here, or a QR code if you'd like to scan that too. And so, yeah, if you have any questions other than that, then that concludes the presentation.
Yeah, I have one quick question. That last demo,
Yes.
you basically trained your own model using that data set that you found related to movie reviews.
Correct.
And so you could, are there a lot of those existing data sets out there for doing sort of similar tasks? It seems like there's just a lot of that common things that you'd want to do on a forum like that, like profanity filtering, for instance. Are there, how do you find data sets like that, I guess?
Yep, great. That's a good question. There's one. Matter of fact, I think, let me go to my browser. I can pull up Kaggle. I don't think I got this one from Kaggle, but I may have. But if I go to Kaggle.com and just go to data sets, there's lots and lots and lots and lots and lots. Right up the way COVID-19, right?
Oh,
Yeah, so yeah, and this is just one example. And Kaggle is a website. This is a community that's dedicated to machine learning and AI. And they have contests. So like every now and then where you can try to perform a task and people compete against each other. It's a very interesting community. So yeah, so this is just one example. And I don't even know how to get to the whole list of it. And you have to search what you're looking for because there's quite a lot. Wine reviews, NBA games, so Google Play Store apps. So, I mean, I'd be willing to bet for if there's a data set that you wanted, you could find it. Or depending on what you're after, you might build it. I remember this is a while ago when I was trying to learn more about this sort of thing. I was looking at my children when they were younger. I was trying to build a prediction model to help figure out what foods they would like and not like. And that was an interesting exercise and kind of really gets you thinking about the questions that come up in exercises like this. So a food that is creamy and hot, like mashed potatoes, has a completely different reaction than something that's creamy and cold, like ice cream. So there's texture, and color. There's so many different things that you don't really think about, and it's hard to put that into a feature set. Like, how do you know what's going to be important unless you try it? And there could be something missing. I don't know, I'm thinking what the example is. Like, I don't know, flotation. There's a very specific formula and predictable set of attributes that determine if an object will float. And it might be the density that water displaces. So you may have access to, let's say there's 4 things that determine if it floats. You may have access to 3. You'll never get that 4th one. So you'll never be able to have something that's as accurate as saying this can float. You'll only be able to have a close guess. And then the higher those things match up, the higher your guess is going to be.
Okay.
Yeah, if that makes sense.
Yeah, really interesting.
Yeah, oh yeah, I think so too. It's the kind of thing that you can start reading it and then, I think I'll just read this for a half hour before I go to bed. And what do you know? It's 2 o'clock in the morning. Yeah. But anyways, yeah, Kaggle's a great resource. There's a lot of stuff out there.
So I propose that we develop a conspiracy model and we put in all the great conspiracies of history and the world in one model and see what it tells us.
Hey, that's great. Or at least be able to filter in what types of conditions in the world are present that spit out the most convincing conspiracy theories.
I'm afraid that we'll find out that all of the conspiracies are true.
Yeah, that's funny. Yeah, it's neat. Yeah, I know, it's just really cool.
Entry is a fake job posting prediction. That might be beneficial.
Fake job. Oh, that is interesting, isn't it? Fake job posting.
Cool.
Oh yeah, that's a good one.
Yeah, good idea.
I like it.
Hey, Mark, this was awesome. I have 2 questions for you.
Yes, sir.
On your sentiment example, could you flip that around? So you were using classification to determine if it was positive or negative. Is that accurate?
Yeah, correct. Yes.
So could you flip that around and instead say of 0 and 1, it's positive or negative, just say, here's the rating associated with them, and then get, use regression, I guess, instead, and get a value coming out that would be like a 0 to 1 or something range, not an exact Boolean, to say where it comes out. So then you'd get kind of okay, this is somewhat positive or somewhat negative. Would that be the approach for that case?
Oh, that would be an excellent approach. And I got to think about that because, and in fact, in a way, IMDb natively does that, don't they? But thinking more about it, if I have a rating from 1 to 10, the 3s and the 7s are going to be easier to tell apart than, say, the 5s and the 6s, and the 6s and the 7s. And I might be able to look and say, this movie is complete crap, and that is a greater negative than, say, I didn't enjoy this movie. That really doesn't affect the quality of the movie whatsoever. It's more of an opinion. So I would suppose, yeah, I mean, the short answer to your question is yes, absolutely. And as my brain's going through it with the data set that we have, let me see if I can bring it up once again.
Well, do you also get back like a weight then? Because to say that it's a 0 or a 10 obviously should have more weight to say we're pretty positive this is really negative, right?
Yep, absolutely, yes. And I'm sure there is a way to derive that from the way that we've implemented it here, but yes, absolutely. But I was thinking that through is even just classification, you could accomplish the same thing. And the model could become sensitized to looking at things that are, one level apart. And it would learn to categorize based on certain attributes. If it's just a profane word, or if there's things that generate an opinion, you could probably do that too. But yeah, regression would be one way to get to a sliding scale, but it could still be classification, sure.
Cool. The second question I have is, once you build these models, like we've talked about Xamarin, and this is mostly a Xamarin group, and once you have the models built, like then they perform quickly once they're built, or does it matter like what type of model it is as to how quickly it performs once the model is actually built?
Yeah, that's a great question. On my PC, they seem to be going rather slow, but that could be just me. I'm prepared to believe that the larger
Even
the
just
data,
to execute the model?
probably, because
Yeah.
I have to think of it that when you're looking at a model to make a prediction, for example, there's some indexing and some things that probably are more straightforward, but the more it has to think, the longer it's going to take. I haven't done any experiments, but I would expect that there's a great deal of variation among performance. I would expect that to be the case.
This is Alan, and from what I've
Hey.
seen, the TensorFlow algorithms do tend to perform faster after you have a trained model. So
Yeah.
it may also depend on which system you're using and going forward with.
Oh, sure.
Yeah,
That's a good point. Oh, I'm sorry, carry on.
So ML.NET, can you tell it to do any execution on the GPU, like you leveraging CUDA or OpenCL?
Sadly, well, I don't believe so. I mean, when I was looking at those types of requirements, GPUs were not supported on ML.NET.
Okay.
But I have seen, and as a matter of fact, I'm doing some experiments right now that you can build a model in TensorFlow for like image recognition, for example, that utilizes GPU processing, and then implement that model on ML.NET. So kind of, I guess, but I don't think really.
Okay. Does ML.NET support tensor cores?
That I don't know.
Okay.
Interesting. I mean, as far as I'm aware, it's just the modeling standpoint, and you're going to send me back to the books on that one, because I know that there's file formats that have some compatibility. Like an Excel file can be opened in OpenOffice as well as Excel, just like this model could be used in TensorFlow as well as ML.NET. I'm not sure it goes any deeper than that, but I don't know for sure.
Interesting. Have you ever heard of UiPath?
UiPath, I have not. What's that one?
The RPA platform, robotic process automation. I'm just curious. I wonder if I probably could integrate ML.NET into UiPath, because it's built on top of Windows workflow and C# and stuff. So, anyways.
Yeah, I mean, yeah, I think that's what I think ML.NET has going for them is, if you've got an established application, you can add in machine learning capabilities just like you'd add any other feature. And I mean, I suppose you could do that anyway if you had like an external API or something, but it can be part of your application, which I think is super cool.
Yes.
Yeah, but I digress.
I love it.
Cool. Yeah, me too. So I'll throw the resources, and let's see if you want to snap it. And like I said, I've got everything on GitHub, the sample applications, if you want to thumb through it on your own.
What was your GitHub?
Oh, it's the MD Kalal.
Oh, at the bottom. Okay,
Yeah.
cool.
All right. Well, cool. Anything else? Any last questions, anybody? I think we're good. All right, everybody unmute and give Mark a big round of applause.
Yeah,
Hey,
that was awesome.
Hey, thanks everyone. Thank you. Thank you so much.
Awesome.
You, Mark.
Thank you, man.
Great presentation. Thank you.
Thank
Good
you,
job,
sir.
Mark.